from EngineSoft, and together with me are the Vice President of Endurica, Tom Ebbott, and my colleague Betty and Pauline from Endurica. He will show how physical testing and simulation can work together to understand and improve the durability of elastomeric materials. If you have a question, type them in the chat, and we will have a Q&A session at the end of the presentation. We can now start the webinar led by Tom.
All right. Thank you, David, and welcome everyone. My name is Tom Ebbott, and I'm from Endurica. And today we're going to talk about what tests should you run to predict elastomer fatigue. I'll be the main presenter. We also have Kurt Miller, president of Axel Products in Ann Arbor, Michigan, here in the States. We have him via recorded video today. So at Endurica, we look at our solutions in four different manners. First and foremost, we provide software for elastomer durability prediction. And we have a number of software products to predict fatigue life, to predict incremental damage, to predict self-heating and oxidation, air diffusion, and then also a module that does fast processing of time-based road loads. So together, that's almost a complete suite of capabilities to predict durability of your elastomer components. We're also the hardware representatives for Coesfeld in the Americas. So we sell hardware from Coesfeld of Dortmund, Germany. We do engineering services in terms of materials characterization, which we'll talk quite a bit about today, but also CAE services, finite element modeling for people, projects, that sort of thing. Finally, we do training, and we do on-site as well as online training and customized training by request. Last year, we had the privilege of being able to start a totally new sister company in Luxembourg. So to better service our customers and prospects in Europe and the EMEA region overall, we have a new company in Luxembourg with people with boots on the ground in that country to better serve the European region. With that, I'm going to let Kurt talk a little bit about Axel Products. So, Kurt.
Hi, this is Kurt Miller. I'm off camera right now. I'll be on camera more than you probably would like. But anyway, Axel Products is a physical testing laboratory in Ann Arbor, Michigan. We have always done the same kinds of things. We develop experiments and we perform experiments for people trying to write math around the behaviors of materials and get them into their finite element code somehow. So a lot of our work traditionally was in elastomers, fatigue, failure of elastomers, hyperelastic characterizations, viscoelastic characterizations, dynamic vibrations, and that sort of thing. We do a lot of work in plastics. We do plastics work at multiple strain rates for crash analysis. We do things like DIC strain processing. We've been doing a lot of work these past few years in adhesives, trying to understand how they work, both in bulk and how their adhesive properties, again, can be put into math models, and the same with foams. We're always trying to do measurements that are meaningful to the analysts so that they can be fitted and squeezed into a math model that describes real behaviors in real analysis.
All right. Thank you, Kurt, for that overview of Axel Products. So here we see the basic workflow for Endurica. And so we need to do a typical finite element analysis of your part or product. And for the input to that, you'll need some information on your geometry, some idea of the stiffness, which we characterize using hyperelasticity, and then some idea of the boundary conditions, like the force history, where it's fixed, displacements, etc. You put that all into the finite element code, and you can predict things like stresses and strains, and sometimes even temperatures. If you do need temperatures, then you also need to have some idea of viscoelasticity from the materials characterization. To do fatigue, we'll need to know something about the crack growth characterization, which we'll talk quite a bit about today, as well as the precursor flaws. Those come into the Endurica solver, Endurica CL, which then predicts the fatigue life for every element in the finite element analysis. And then the element that has the minimum life is going to be the one that's controlling. You can take that information, paint it back on your finite element model to visualize, where the most damage is going to occur and where the first element is going to fail in your finite element model. So these are the areas we're going to concentrate on today: hyperelasticity, crack growth, and precursor flaws. So, you can also think about things like viscoelasticity and aging. We'll save those topics for another webinar. So we'll start with hyperelasticity. Um, in hyperelasticity, you're typically looking for a strain energy density function, W. That's a function of the strains. In this case, we're using the stretch ratio lambda as a strain measure. It's the final length divided by the initial length. So if you think about putting a 10% engineering strain on a specimen, the lambda is going to be 1.1 for that 10% engineering strain. Sometimes it's convenient to write this not in terms of the lambdas directly, but in terms of strain invariance. So here are these strain invariants listed, but it's the same kind of result. We're looking at what's the strain energy density in terms of the deformations of the specimen or the product. Once we have that function W, you can differentiate it with respect to the strains, in this case with respect to the stretch ratios, and get a stress-strain relationship. Most simple form of W that we have is one that has a single coefficient for stiffness. In this case, C10. We'll see why it's 10 in a minute. And times only one term in one invariant, I1. We subtract off 3 because when there's 0 strain, lambda equals 1. So I1 equals 1 plus 1 plus 1, or 3. So we subtract off 3. So this argument goes to 0 when the strains go to 0. I can then differentiate this W with respect to the lambdas and come up with a simple stress-strain relationship in simple tension, as an example. Okay, rubber is often very hard to change the volume in rubber. So we treat it oftentimes as nearly incompressible. Sometimes people treat it as exactly incompressible, but in finite element models, sometimes that creates convergence problems. So it's best oftentimes to have some amount of compressibility, but we do that by treating the compressible part and the incompressible part separately. So we characterize the volume change by a parameter called J, and you can convince yourself that lambda 1 times lambda 2 times lambda 3 gives you an indication of the volume in the specimen. Now we want the volume due to the elastic energy, not due to something like thermal expansion or contraction. So we take out the thermal effects and just look at this J elastic to characterize or measure the volume change. Associated with the volume change overall are the extension ratios. And now we're going to define the lambda bars, which are the extension ratios for the volume conserving part of the deformation. And they're by this expression, so that lambda 1 times lambda 2 times lambda 3 bar are always equal to 1, and this is the volumes conserved. There's a couple of forms here for W with this nearly incompressible form. Here's a general polynomial. You can see if I just take the first term, I is equal to 1, J is equal to 0, I get C10, I1 bar minus 3 to the first power, and that's the Neo-Hookean law we saw previously. And you can take as many of these terms as you want. You'll just need to be careful in characterizing the coefficients that you maintain the response that you want. So this is the volume conserving portion. The volume changing portion then is here, where we have the measure of the volume change, J elastic, and then a coefficient D, which is the material property characterizing for a given amount of strain, how much volume change do I get? So 1 over D is like the bulk modulus. You can think about it as a material property. And in rubber, the bulk modulus is something like 1,000 times the shear modulus, which is something like the C10. In Endurica, we often use an Ogden model, which is written not in terms of the strain invariance, but in terms of the stretch ratios lambda. Um, so if we think about characterizing this function W with respect to two variables, here we're doing it with respect to two stretch ratios, you get some type of response surface for W. If you just do one experiment, you'll just have one line on this response surface and you won't know kind of what the rest of the surface looks like. So it's good to do experiments in different modes of deformation. So here we have uniaxial tension, like a small specimen like this. And then we introduce planar tension, which is a kind of a very wide and not so tall specimen that we'll pull in the vertical direction. And then an equibiaxial test that we'll do, which will give us a better idea of this overall response surface. Here we see some stress strain results for those tests in simple tension, planar tension, and biaxial tension, along with the amount that the rubber softens. So there's something called Mullins effect, where if I pull it once, it softens, and the second pull is not as stiff as the first, etc. And we also characterize that Mullins softening. So in order to describe more about these experiments, I'm going to go back to Kurt Miller. So, Kurt.
Okay, excellent. One of the things that we're trying to do with our experiments is we're trying to relate stress and strain in the material to fracture mechanics properties, how a crack starts, how a crack grows. So the first order of business is we really have to do a great job of understanding the stress and the strain condition in our part if we have any hope of predicting fatigue properties. So the first order of the day is to get really great descriptions of, in this case, it's rubber, so the hyperelastic properties. As Tom just mentioned, the best thing to do is to get multiple states of strain, because when we deform rubber in an application, it's just never simple. Because the material is incompressible, as soon as I compress it one way, it goes other directions. If I shear it, there's always some tension, there's some compression. It's always big, messy business in there. So we have to have hyperelastic models, which are awesome. However, hyperelastic models need multiple data sets in order to characterize them well. If you don't have very much data, you have to use hyperelastic models that are not very descriptive. And because we care a lot about high strain and high stress points where fatigue may happen or failure may happen, we really want to have great hyperelastic material models. And so we're going to do experiments. Now, these experiments are a little different than plastic and rubber, plastic and steel experiments, in that what we're trying to do is we're trying to put the elastomer in a particular state of strain so that we can use this so that it can be described with a closed form math solution. So when we're in tension, I've got this little tensile bar here. And so when I stretch this, I'm assuming that when I stretch it, it's free from any constraints on the sides. And that means it's very long, typically 10 times or more greater than the length or the width, so that we're not constrained by any effects on the ends. Because it's a pure state of tension, I can write some math and I can start optimizing an equation around that. Garden variety tensile tester, it's a crosshead, load cell, is a specimen. And you'll notice there's two stickers on the specimen. In this case here, we're using a big laser. So this is a laser extensometer to measure the strain on the specimen. It's absolutely critical that we measure strain with a non-contacting device. That's very old world to be grabbing specimens. It's not okay to assume that the crosshead travel is correct. So we have to do this. I'm not going to say any more about that. That's kind of old news. So here we have our specimen in the machine. It's got the two stickers. Laser extensometer is going to measure the strain. So right now, I'm just going to start a test running. We're going to look at the screen. Then, because we have a lot of material to jam into an hour, we're not going to stay too long with that. So right now, I don't know if you can tell, but that crosshead is moving. And what I've done is I've stretched to 30%. Now I'm unloading back to a near zero stress. And I'll talk about why that's important in a second. The really important thing is that we have put the rubber into a state of tension so we can write math around it. All right, I'm going to sneak over to the video. So what we have here is the image on the screen. So we loaded, we unloaded, we loaded, and now we're unloading. So a couple things to notice is the first curve, first time we load, does not look like the second time we load. Also, stretching is not the same as unstretching. There's some viscoelastic behavior there. This time, we're going to go from all the way up to 50%. We were just at 30% strain. So the material changes quite a lot depending on how much it's been stretched. Notice also that we started here, and when we unloaded it, it does not fully recover. So even with very elastomeric elastomers, there can be a little bit of set. As analysts, we have to decide whether I don't care, I'm just going to ignore that and get on with my life, or it's so significant I have to make provisions for that. So there's a lot here right now. So we have the first time loading where it's stiff, second time loading where it's softer. If we stretch it farther, it gets softer again, and loading and unloading are different. A lot of the behaviors of rubber are right in front of you right now. So Tom mentioned the importance of multiple states of strain, tension, shear, and biax, all extremely important. Also important to understand the loading conditions of the material and what effect that has on stress strain. And so the math model that is often used for fatigue, and I know that Endurica uses, is an Ogden-Roxburgh model, which basically is Mullen's softening. So the material model will actually soften the behavior mathematically, just like we see on the screen here. So what we just saw was a tensile test, very long. When I stretch it, it's unconstrained on the sides, and we see loading behaviors. We see softening, we see viscoelastic behavior, we see a little bit of set, which we hope isn't too big, and it's going to go farther again, and I'm going to move on. I'm going to move on now to the next experiment. Talk about different states of strain. One very important state of strain is you'd say it was compression. Hey, my part is always in compression. Yet, when we try to do compression experimentally in the laboratory, it just doesn't work. So, if you imagine this is a hockey puck, if I compress this hockey puck, the sides move out. But unfortunately, between my hands and the hockey puck, there's friction. And so when I compress it, it kind of bulges, and that makes a big mess experimentally. So it's not perfectly just compression. It's compression with some shearing and some other messy business. So instead of compressing the hockey puck and getting the sides to squeeze out, and I suffer from a lot of friction, instead I'm just going to grab the perimeter of this thing, stretch it, and this top and the bottom will come together. So instead of using the disc, I'm going to use this shape. I'm going to take this shape, I'm going to pull on all the arms and stretch it. And when I do that, top and the bottom of the specimen will come together. So if you're like a little piece of rubber living in the center there, you really don't know whether you're being compressed or whether you're being biaxially stretched. And so I'm going to rotate the camera here. What we have going on is we have a biaxial test running. Let's see how I do here. The two stickers on the surface are to measure strain, and the entire region in the specimen is all being equally biaxially stretched. Honestly, we could measure strain between any 2 points we want. So once again, there's a laser extensometer looking down on the surface. So that's the biaxial test. And I'm also going to show you the screen. Wasn't very interesting because I was just trying to do this for a demo today. Here's the loading unloading pattern. We were just going to 50% and back, 50% and back, just so that it could be running and I could walk up at any moment and have something to show you. But again, first time loading is stiffer, softer, unloading, set. All the same things we saw in tension. So that's the biaxial extension test. Okay, we're going to travel a little bit now. I just came up to another tensile tester. We back up a second. You see it's a tensile tester. Cells on the top, crossheads moving. And there's a specimen. And the specimen that's in there right now looks like this. It's very wide, not very high. When we stretch this specimen, because it's very wide and not very high, we are trying to achieve a condition where, because it's really wide and it can't move, let's just say left and right on your screen, it can't strain, all the thinning occurs in one direction. So when I stretch it, it gets thinner only front to back. There's no sucking in on the sides. Of course, there is a teeny weeny little bit, but we're going to pretend that's not happening. So once again, we see a specimen in there. We see two laser stickers because we're measuring using non-contacting measurement to do it. And by the way, a question that I've often asked is, could I be using a video extensometer? Answer, yes, absolutely. And we do sometimes. Laser extensometers are really awesome because they always work and they're really reliable and they go through multiple layers of glass for chambers. But yeah, video extensometers work just great for this. And so right now, it's very hard to see. It's hard for me to even see standing here, but same idea. Right now, we are loading and unloading the specimen. Walk you over to the screen for a second. Okay. All right. We saw tension. We saw biaxial. We saw that this is planar tension. Some people often call it pure shear. The real important thing is, because we're assuming it doesn't move in on the sides, because it's basically infinitely wide compared to its height. There's a closed form mass solution, and the tension test, the biaxial test, and the planar test all have closed form solutions, and we can numerically fit them with an optimizer, and they all fit nicely on the blue surface that Tom showed a couple slides ago. All right. I'm going to show another test, kind of a strange way, because it's actually not much to see anyway. So what we have here is, this is a fixture that we use for the bulk modulus test or the volumetric compression test. And what we do here is we take little discs of rubber and we just stuff them into that little hole on top. Then we take a plunger which fits perfectly. You can see it's an air fit. It doesn't even drop in because it bounces on air. And we're going to use a laser extensometer to measure between the fixture and the pin. And we're going to compress that rubber and see how incompressible it is. That's kind of a crazy idea. We're going to compress it because it's incompressible. But that's pretty much what we're doing. We're kind of trying to see if it's a teeny weeny bit incompressible because it matters. Now, just an aside, I'm going to attempt to show you a piece of paper. I don't know how well this will fly. I can always send it. It's this. This is my favorite graph. So if I can sit still. On the right-hand side of on your screen, the bottom curve is a compression test. The top curve right here is volumetric compression. That's the stiffness difference between bulk stiffness and compression or basic shearing. It's massive. So when we talk about rubbers not wanting to change their volume, we're not kidding. It doesn't want to change its volume. It's enormously stiff when constrained. And you might say, who cares? My rubber's in compression, my part's in compression. You do care because everywhere the rubber is bonded or in frictional contact, the rubber near that surface is in fact experiencing the bulk bounce. Okay, I have nothing else to say on this topic. Tom?
Thanks, Kurt, for that. And now we're going to move on to fracture mechanics. So fracture mechanics started its birth in the 1920s with a man called Alan Griffith, who came up with the concept of energy release rate, sometimes denoted by a script G. That concept was extended to rubbers by Alan Thomas and Ronald Rivlin, and with their paper published in 1953, where they said the tearing energy in a structure is like the change in the strain energy divided by the change in crack area. So if you think about holding a specimen like this, or deforming it very slowly with a fixed displacement, at some point that crack will move a slight amount. When the crack moves, the total energy in the specimen is going to go down because the crack has made the total structure more compliant. So the total strain energy goes down, and as the crack increases by amount delta A. So the amount that energy goes down divided by the crack area change, delta A, is this quantity, tearing energy or energy release rate. So the value of this tearing energy is like it's like the level of stress or strain in your product, and it changes throughout the product due to the geometry and the loading, and they all have some level. When that level reaches a critical value, say the tear strength of the critical tearing energy, that now is a material property. It's like the ultimate strength or the yield strength for metals. It's the property, the level of tearing energy at which a crack will start to grow. So that's an important quantity to know for your material. We also see that this tearing energy or energy release rate also characterizes well the crack growth rate, the amount of crack growth with respect to cycles for a fatigue loading situation where we have cyclic loading, where the maximum tearing energy is going to be well below T sub C, but due to the number of cycles, you're going to get some crack growth. So we'll see a lot more on this curve later on, but this is crack growth rate versus energy release rate, typically plotted on a log-log plot. They used funny units that we don't use anymore back in 1964. So we'll use the same specimen that Kurt showed for the planar tension, but now we're going to introduce a crack on the side of that specimen. And we can easily derive the value of tearing energy for this specimen by considering the fact that, okay, we're loaded in the vertical direction. We're going to have this homogeneous area of strain energy density here, and it's going to be unloaded here. So as the crack grows by an amount delta C, the volume of this area that's loaded with the strain energy density W is going to go down by this volume dictated by delta C. So that volume is delta C times the thickness of the specimen times the height H. And then I multiply that volume times the strain energy density, and I get the total change in the energy. The change in the crack area then is just delta C times the thickness. So I plug those in, I cancel out the T's and the delta C's, and I see that the tearing energy or the energy release rate is simply W, the strain energy density in this homogeneous region, times the original height, H. And it's good to acknowledge that in this specimen, the tearing energy is independent of crack length. So when we use this in experiments, we can directly change the tearing energy level just by changing the strain in the specimen, and it doesn't matter what the crack length is. All right, our target for this crack growth rate characterization, fracture characterization, is the following curve. So we've got one limit is the T sub C, the critical value, which starts a crack propagating with a single pull, and that's T sub C, that's one limit. And then if we go below T sub C, we tend to see data that falls along a straight line on a log-log plot, so that you could think about a power law being able to characterize or represent the data along this area where we have a slope F. If we get down low enough, we're going to approach another asymptote, which is dictated by something called the intrinsic strength T naught, also called the fatigue threshold. You can think of this value like in metals, you'll have a stress amplitude versus life plot. And if you go down to a certain stress amplitude, the life goes on forever. And that amplitude is called the endurance limit. So this is like the endurance limit for metals, this intrinsic strength for rubber, below which you supposedly don't have any damage or crack growth. You do have to be careful though, because with something like aging, this material property T naught can decrease, and you might be in a place where you thought you weren't going to get any damage, but all of a sudden with aging, now you might get some damage. So that's an important point to keep in mind. So our target is to look at this whole curve. Let's start looking at experiments for T sub C. So we can take our typical fracture, pure shear or planar tension fracture specimen, and we can pull it slowly in the vertical direction and tell one of two things. One, we'll watch the crack visibly and see when it starts to grow. Or number two, we can get a blip on the stress strain response that we're looking at, and we can see that a stress drop is an indication of the crack growing. Now the stress might continue to rise after that because the crack might not grow in a self-similar manner. It might grow crooked, or the crack might blunt, etc. But whenever the crack starts to grow, the experiment is over, and that's the definition where we look at the strain energy density at that point W, multiply it by the height H, and get the value of T sub C. All right, so when we do crack growth rate testing with fatigue experiment, so now we're going to be thinking about oscillating something like strain as time goes on. And this is a chart that I just stole from Kurt off a whiteboard that he keeps in his laboratory. So we're going to be applying an oscillatory strain so that T is kept below T sub C, but we're still going to get crack growth in this fatigue sense. So the crack is going to be growing even though the tearing energy in the structure is below T sub C. And that is going to be used then to measure, we'll have a video system set up that will measure the crack length over time. And we're going to use a ramp procedure where we start at a very low strain somewhere down in this region and then ramp it up to a strain corresponding to T sub C. So we know where that strain is because we just did this single pole fracture test, and we know the strain at break when the crack started to grow at the point T sub C. So we're going to go up until, but not over that, because that's when we get a lot of crack growth with a single pull. So we use this ramp procedure in Endurica where you continually increase the amplitude of the strain throughout the test. This runs for about 20 hours, and about 8 hertz is usually the frequency that we use in the fatigue. So the data usually falls along a straight line on a log-log plot, and you're able to characterize it by a power law relationship where we get the crack growth rate to CDN is equal to some coefficient R sub C, T max divided by the material property T sub C to the power F. R sub C is then the value of the crack growth rate when T is equal to T sub C. So right out here somewhere, you get this intercept, and that's the value of R sub C, usually around 10 to the minus 2 millimeters per cycle. One other behavior that we get when we think about materials that can go through something called strain-induced crystallization is that if you have something like a natural rubber, where if I stretch this a lot, or you can think of high strains at the crack tip, that the polymer chains themselves are going to start to align with the loading, and certain elastomers allow these polymer chains to form crystalline regions. So these crystalline regions then form an inhibitor to any cracks propagating perpendicular to them. And you can also think of having anisotropic strength where it might be easier to go sideways. And you can kind of see that with a lot of crack branching in this experiment that was done on natural rubber for a non-zero positive loading. We indicate the amount of non-zero loading by this R ratio, which is the ratio of the minimum tearing energy to the maximum. So if this is greater than 0, it means that we're keeping the part in tension. And if we do get the strain-induced crystallization, we should get some benefit in terms of durability for keeping it in tension. This is much different than a metal, where if you keep a metal in tension, the crack's going to go faster. And things like natural rubber, if you keep it in tension, the crack actually grows slower. So we can see that in these charts for two elastomers. This is SBR, styrene butadiene rubber, run at different values of R ratio. We see that all the data lies along the same straight line on the log-log plot, so there's no real benefit for keeping in tension. For natural rubber, however, when we increase R from 0 to something fairly small like 0.05 of the ratio, we see this large effect going from the blue curve to the pink curve with almost an order of magnitude benefit in terms of crack growth rate of keeping it in tension. So with that, I'm going to go back to Kurt to talk about the fracture and fatigue experiments. So Kurt, take it away.
Okay, so I cheated in the sense that I didn't change it, put a new specimen in this instrument. I just left the one that was in there. However, I put a crack in it. So here we are again, chamber, load cell, test machine, laser, all the basic stuff. And so I'm going to sneak the camera forward and see if I can get you to see what I see. So I'm hoping that you can see a crack there. I put that crack in there with a scalpel as best I could. I didn't do a very good job. Our people that run these tests here would be a little disappointed in me, but nonetheless, here it is. I put a cut in there with the same planar specimen. I'm gonna put the flashlight aside for a second and start the crosshead. So right now, the crosshead is moving, going kind of fast. So here's the key thing. That crack is opening, it's opening, it's opening. And, you know, I don't know what rubber I have in here, so I haven't a clue what this thing's going to do, whether it's going to split or grow or what. That crack has already started to advance. It's gone through that white line, which was the 20 millimeter from the side line that I put in it. So the test is over. So the instant that crack advances, we just determined, oh, that's pretty cool. Always fun to see things fail. So specimen broke into a funny shape. But so the instant that crack moves, that's our critical tearing energy. In other words, we're not fatiguing. It's not a crack growth test. It's just like, that's how much stress, that's how much strain it took on this specimen just now to advance. So that becomes, you know, if that occurs in your part, obviously you've got a problem, your crack is growing. And so if that occurs on a part, then, you know, things are over. Step before for screw machines, like slow install machines that don't
I skipped over this one.
And they're really good for static tests, but they're extremely good for static tests. This is something a little different. This is a hydraulic actuator. This grip goes up and down. It can go up and down extremely fast. A very, very active system. In this case, the load cell is on the bottom. And we have, again, our planar tension specimen. What we're doing in this experiment right now, you can see there's a crack. Sneak you up forward, but you actually can see that there's a crack instead of me just telling you. This crack has grown quite a bit. It's growing all night.
Usually this is 8 hertz.
Now that crack grew, and it grew faster and faster and faster. And I'm going to show you a chart, which is really the same thing that Tom showed you a moment ago. I'm going to force you to see it again because it's worth seeing again.
Exactly the same.
And what we have here is strain, time. And the experiment that we do is we are running a sine wave into the rubber. We're unloading to zero force, called it strain, but it's basically zero force, zero strain. And we simply keep making the amplitude larger and larger and larger over, say, a 20-hour period. And we know that we don't have to cycle at all to get it to fail at the critical tearing energy or the critical area strain. So this right here is really T sub C. So there's no sense cycling the levels beyond which it would just grow anyway. So the default test plan is we cycle for 20 hours up to the critical tearing energy, slowly ramping during that time. And what happens is, as the ramp gets bigger and bigger, maybe it's a surprise, maybe it should be no surprise, this is the size of the crack. So early on, the crack doesn't care. It just sits there happily, doesn't move. And gradually, the crack begins to grow, and it goes faster and faster and faster. It's absolutely a wonder of the universe to me how many elastomers just follow this beautiful polar law relationship. And it's like, holy cats, whoever figured that one out. It's brilliant. So anyway, awesome, very convenient. So that is that. And I'm gonna just pick up a computer behind me here. This is the experiment that was running during the night. So this is sort of the machine software. And so this is the crack growing. This is reality. This happened last night on a real elastomer. And right here is the last measurement of a crack. So we have an imaging system behind the crack that keeps taking pictures of the crack. Now this is kind of a boring crack. It's kind of just going straight across, which is exactly what's happening, but it's really, to me, it's kind of boring. So the crack's just going straight across, and then the tip of this crack is basically what we're calling the crack width.
Okay, so that's the demo of the fatigue experiments. So if you think about doing fatigue life calculations, we're going to take that power law relationship and we're going to integrate dc dn, put the dn over here, and solve for the cycles of failure. So we're going to integrate from the C naught to CF. CF can be something like 1 millimeter by default or some other length scale in your part. But what is C naught? In rubber, there's typically crack precursors due to various, things about the material, like the carbon black agglomerates or the particulate additives or scratches or things like that. And these precursors typically go from 1 micron to 100 microns. And that precursor flaw is from where cracks start. So we use a certain series of experiments in order to determine what this crack precursor is without trying to go and look for it with a microscope, which would be very difficult to find out where's that largest precursor. So the way that we do this, and all the founding fathers kind of agree that the nucleation of crack growth and the growth of large cracks is the same process in elastomers. So here's our typical dCdN versus tearing energy plot that we just talked about. Here now is another plot like an SN plot in metals. So we're taking a typical dumbbell specimen with no crack and just cycling it to failure and plotting the number of cycles to failure versus different levels of the tearing energy. So there is a certain value of C naught that we can use that when we integrate this with the value of tearing energy that we're applying, we do this integral, that C naught value is going to give us an N sub F that's going to lie and agree with the data. So we're predicting the cycles of failure experiment from the crack growth information, and we're predicting that by looking for the value of C naught that makes our prediction in the red line line up with the data in the black. So that's how we determine C naught, the precursor, and we do a number of experiments. Typical. That's pretty noisy, but this is just a fatigue to failure test. There's 3 specimens here. There's others that have large banks of this. It's just testing fatigue to failure. When we plot this on a strain life diagram, just like we saw before, and we look for different values of C naught, each value of C naught is going to give us a different curve here, and the one that matches with the data the best is the one that we're going to call the C naught we're going to use, in this case, 23 microns. Okay, so we've got T sub C, we've got the power law area, and now we're getting down towards, a lot of times your part is going to hopefully be operating close or below T naught. I hope your part's not operating somewhere in the upper part of this slope F, because the test that we ran to characterize that only ran for 20 hours. So yeah, I imagine your product needs to last for more than 20 hours. So it's important to know the lower end of this curve as well. We do that by characterizing this quantity T naught, the intrinsic strength. One way to do that would be to run very, very long fatigue experiments. So here's Radek Stochek and his collaborators ran some very long experiments on EPDM. EPDM doesn't age in air, so you can run very long experiments and you can get some value of T naught here, which was about 47.7 joules per meter squared. So T naught is typically on the order of 50 joules per meter squared. T sub C, on the other hand, is something on the order of 20 kilojoules per meter squared. So you can see a huge difference between T sub C and T naught. So there's different ways of measuring T naught. One is by this near threshold, which takes many, many months. You can do it by swelling. You try to get rid of the hysteresis in front of the crack tip, because it's this hysteresis and energy loss that contributes to the very high values, say, that you see in T sub C. So another way is doing swelling or high temperatures. What we use is a cutting method. So we're going to take a razor blade and actually cut into the specimen and look for a minimum amount of energy in order to do that cutting, and relate that cutting energy back to the T naught tearing energy by a correlation curve that's been done by Lake and Yo some years ago that fits many different polymers. So that's how we go about determining T naught. Okay. You can do this in the pure shear specimen like Kurt did, or Coesfeld makes a machine that automates this process and determines this T naught as well as T sub C for you. And Coesfeld markets that, and we sell this machine in the States. So I'll just put a little bit of a plug-in for the Coesfeld instruments. Again, the company is in Germany. Here's a tear and fatigue analyzer that'll do the crack growth testing for you, 2 different flavors of it. Here's the intrinsic strength analyzer that determines T naught as well as TC. Here's a machine called the instrumented cut and chip analyzer. Here's another one if you're interested in heat buildup and for things like tires and other places where you have contact and friction. Friction is also very important. So Coesfeld does a nice job of creating these nice machines specifically for rubber and some for plastics. I talked a little bit about aging. I'm going to leave aging for another lecture, another webinar, but you certainly can get changes in things like T sub C and T naught due to age. Typically, they go down, right? If you get oxidation, or even if you have anaerobic aging without oxygen, you can have rearrangement of crosslinks, and you can have aging that you'll need to characterize and to know what's my CDN versus energy release rate curve for my aged material. We typically create master curves for stiffness, intrinsic strength, and fatigue strength, or critical energy release rate, turn strength, due to aging time. Typically, you'll do aging at higher temperatures for shorter amount of time in order to predict what happens at longer amounts of time at lower temperatures. So in Endurica, together with Axel and our partner labs, we have a full range of characterizations that are available. We talked mostly about hyperelastic and the core fatigue module today, together with the intrinsic strength and the non-relaxing module. But as you can see, there's a host of other modules that are available that we can discuss if you have any questions. We also produce reports, do the data reduction, nice plots, snippets of input files that go directly into our codes, and you can find more about this on our website. So with that, I'd like to start the Q&A session that ends the formal part of our webinar. So please put your questions into the Q&A bar. I'm going to stop sharing because that's the way that I can see what's in the Q&A area. So let me do that and go back and be able to look at the Q&A. So please put your questions, use the Q&A to put your questions in.
Pauline Glaza here from Endurica. Tom, over in the Q&A part, are you able to see the one question? It says answered, but we promised to answer it at this point.
Yeah. So there's one question I can see. Since the cycling of material is going to be at high strain rates, will it be a good idea to fit hyperelastic models to high strain rates rather than the quasi-static that we saw? So yeah, that's a great question. So yeah, what we saw was sort of a quasi-static characterization of the hyperelastic model. And we can either do that at different rates, if that's important, or we do other experiments that characterize the rate dependence. Specifically, one experiment that we also do is kind of a DMA type experiment where we've got kind of small rubber specimens, and then this is cycled in a oscillatory fashion at different frequencies. So you can get the rate dependence idea from an experiment like this, or you can do, the hyperelastic characterization at different frequencies. We've even done the hyperelastic characterization directly under sort of post loading, because sometimes you get some applications that have, a pulse as part of the product's service loading. So yeah, we can do that, and that's a great question. Okay, I see another question. Why is the Mullen effect critical in durability prediction? Can you brief a bit more? So you want to know what your rubber is actually seeing in your part. And so if you've got something like a tire, or you've got a bushing, every region of the tire is going to have a different stress strain history. And that stress strain history is going to dictate how much the material has softened. So you're actually on this softened curve, and each element in your finite element analysis is going to have a different softened curve given by that Mullen's parameter softening. So depending on the maximum strain or the maximum strain energy density each element has ever seen is going to dictate which softened curve you're on. So it's important to know exactly which stress strain curve you're on, both in your finite element solution as well as in the Endurica fatigue solution, because it's the area under that curve or the strain energy density that's going to be used to calculate the tearing energy for every element. Okay. Also regarding the SN curve, the S is the stress at which the component fails fully. Thank you. So I mentioned SN curves briefly because we use those to look at the cycles to failure to calculate the precursor size C naught. So when we do these tests, the S is really strain. It's really a strain life plot that we use together with the crack growth rate versus energy release rate plots. So we don't use the SN curves directly with finite element techniques. We use them as a way to define the value of the precursor flaw, C naught. Yeah, thank you. Okay. I think that's the questions that I see. Does anybody have any further questions? If not, if there's no further questions, then David, anything more from EngineSoft? Turn it back over to you.
Okay. Okay, thanks, Tom. Thank you, Tom, for your very clear and interesting presentation. It seems that there are no more questions at the moment, so we'll move to the closing part of the webinar. If you think of any question later, you can contact us directly our website. Thank you, everyone.